Welcome back everyone. In this lecture, we'll learn about periodic noise, estimation of noise parameters, restoration in the presence of noise only by using spatial filtering techniques such as mean filters, order statistic filters, and alpha trimmed mean filters. In the previous lecture, we studied about various noise models which were basically uncorrelated with the pixel values. Now we'll study the periodic noise, which is somewhat different compared to the uh, types we studied till now. Okay, so let's learn about it. So the periodic noise is basically generated by electrical or electromechanical interference during image acquisition. And the typical characteristics of periodic noise is it is spatially dependent, which is different from the ones we studied in the noise models, which were spatially independent. So this periodic noise is spatially dependent, and it is periodic. That means it's easy to observe in frequency domain. And the processing method for periodic noise means the way to remove it is basically suppressing the noise component in frequency domain. So we plot the DFD of the image and observe the spectrum and remove those spectral or frequency components which are noise, okay, in the frequency domain, and then convert it back to spatial domain. That is how we do the processing here for the periodic noise. Let us take a look at one example for periodic noise. So this is the image corrupted by sinusoidal noise. You can see the repeating patterns here. Okay, so the patterns are consistent, and you can say that they are periodic. Okay, because the same thing is repeating. Now, if you take the Fourier transform for this, if you take the DFT and view it in frequency domain, then this will be the spectrum. Okay, here the uh, pair of conjugate impulses correspond to one sine wave. Okay, and you can see these dots. Okay, uh, impulses around it, and periodic noise basically looks like dots in the frequency domain. So this is where we can target, as we have studied already. The origin is basically zero frequency. As you move away, you get low frequencies, and move further away, you get high frequency components, right? So origin, so any direction you move, as you move away, you get higher and higher frequencies. So you can zero in on one particular frequency here. Okay, for this ring, you can identify what frequency it is, and you can just suppress this particular frequency to get rid of the uh, noise here. So let us understand how to estimate the noise parameters if we are given a noisy looking image. In the first case, if it is periodic noise, it will be quite evident from its frequency spectrum. Just take the DFD of the image and observe the frequency spectrum, and if it is periodic noise, it will be quite evident in the frequency domain. In rare cases, as we saw in the previous example, it can be identified in the spatial domain also, but it's very rare to observe a noise or periodic noise in the uh, spatial domain. So in frequency domain, it will be quite evident. And in the second case, if it is a random noise with the unknown PDFs, then if we have the imaging system available, so that means the case one, uh, then what we can do is we can capture the images of flat environment. Uh, flat means the region of equal intensity. There is no variation, absolutely no variation within that area, and we capture that particular part using the imaging system. In the second case, if we are not having the imaging system, but we just have the noisy images available, then what we can do is we can take a strip from the constant area and then draw the histogram, and we can observe it. And then we can measure the mean and variance to estimate the noise parameters. This is how the things are done. Let us consider one example for estimation of noise parameters. So this is the test image and its histogram which we have already seen in the previous lecture. So basically we are plotting the entire image histogram at once. Now instead of this, we'll consider one particular strip of plane area or flat area and then plot its histogram. So something like this one. Okay, so I'm just considering one particular strip, okay, around here. So this piece is here, and if I plot the histogram of it, this will be the outline. Okay, or for this image this will be the outline, and you can see the shape is quite evident here for Rayleigh or Gaussian. So it is better to use the histogram of one area of an image that has constant intensity to estimate the PDF. Now that we have learned about various noise models and how it affects the outcome of the image and how to identify or estimate the noise, let us learn about restoration in the presence of noise only. So for that, we use the spatial filtering technique. So when only degradation present in an image is noise, the degradation model we have is g of xy equal to f of xy convolution h of xy plus eta of x comma y. Now here we are discussing only about restoration in the presence of noise. So we'll consider only this part. Okay. So we'll not touch this degradation function. Okay. We'll talk about it later in the module. So we'll focus only on this noise part and its removal. So spatial filtering is the method of choice in situations when only additive noise is present. And in this particular case, enhancement and restoration become almost indistinguishable. First type of filters we are going to learn for image restoration are the mean filters. So basically they are the noise reduction spatial filters. So first type of mean we can have is the arithmetic mean, or basically it's the moving average filter that we have studied in depth in last module. So we take the summation over the window. If it is 3 cross 3 window, we'll take the average of 9 pixels. If it is 5 cross 5, we'll take the average of 25 pixels. Then another mean filter we can have is the geometric mean filter. So given by this equation, f cap of xy equal to pi of g of st. So this pi symbol is for multiplications. So summation is for additions. So this pi is for multiplications raised to 1 by mn. And mn is the size of the moving window. And this geometric mean filter achieves smoothing comparable to arithmetic mean filter, but it tends to lose less image details in the process. So we'll see that with an example. So here in this example, we have the original image of a PCB. Then we corrupt this image with some AWGN, which is additive white Gaussian noise. Now, if you filter the image using 3 cross 3 arithmetic mean filter, this is the result, and it performs quite okay. Okay, so this kind of noise is somewhat removed here in this arithmetic mean filter. Basically, it smoothens out the image. Now, look at the result obtained by using a 3 cross 3 geometric mean filter, and uh, it is a little bit better than the arithmetic mean filter in the sense it loses less image details. Okay, so the uh, objects are a bit more clear here. Okay, the edges are retained a little bit compared to this one. So the image details are retained by the geometric mean filter compared to the arithmetic mean filter. Next type of mean filters we are going to learn are the harmonic and contra harmonic filters. So the harmonic mean filter is given by this equation f cap of xy equal to m into n by summation of 1 by g of s comma t, and mn is the size of the moving window which can be 3 cross 3 or 5 cross 5, And this harmonic mean filter works well for the salt noise. Okay, we have seen the salt and pepper noise. Salt means the white pixels or the white impulses, and pepper means the black impulses. So it works well for the salt noise, but it fails for pepper noise, and it works well for the Gaussian noise. And the second type of harmonic is the Contra harmonic filter. The equation is given by summation of g of s comma t raised to q plus 1 divided by summation of g of s comma t raised to q. And here q is the filter order. And there is a trick with this. The harmonic mean filter worked well for salt noise. So in the case of contra harmonic mean filter, it reduces salt and pepper noise. But there's a catch here. The positive Q is suitable for eliminating pepper noise, and the negative Q value is suitable for eliminating salt noise. And it cannot do both simultaneously. You cannot use the contra harmonic mean filter to remove the salt and pepper noise together. You can either remove salt noise or pepper noise depending on the value of Q. If it is positive, it will eliminate pepper noise. If it is negative, it will remove salt noise. And for Q equal to 0, the filter reduces to an arithmetic mean filter, and for Q equal to -1, the filter reduces to a harmonic mean filter. So let us understand the working of harmonic and contra harmonic filters with an example. So we have a image corrupted by pepper noise with probability of 0.1. So this is the PCB circuit with the pepper noise added in it. Now if you filter it using a contra harmonic mean filter with Q equal to 1.5, this is the result. Look at the effect. The image almost looks clean, and you won't see any type of the noise here. Okay, now if you add salt noise with the probability 0.1, so you get this image. This is a noisy image. Compare the salt noise and the pepper noise here. So salt noise white dots, pepper noise black dots here. Now if you use uh, Q equal to -1.5, it is better for removing the salt noise. Okay, so you can see the result here. So again, the image has improved quite a lot, and you don't see any type of salt noise in the filtered image. So this is the use of contra harmonic mean filter. Now let us check what happens with the incorrect use of a contra harmonic mean filter. So we'll stick with the same example. So image corrupted by pepper noise with probability 0.1, and if you use q value -1.5 for this image, if you recall, q value is negative, works well for salt noise, but it doesn't work for pepper noise. So let's see what is the effect. So this is the effect. Okay, so if you use a negative q value for removing pepper noise, it won't work. And similarly, if you have a salt noise added to the image, and if you use a positive Q values, again, the image will be further ruined. It won't work. Okay, so this we need to keep in mind all the time. So that means contra harmonic filters work well for removing salt or pepper noise depending on the Q value. We have to be very careful in choosing the Q values while filtering. Next type of filters that we can use for restoration in the presence of noise is order statistic filters. We have already studied about it in previous module, so we'll take a quick revisit on the topic. So basically what we do is we have a original image, and we have a moving window, and then we take that as sub image, and then we take the statistic parameters like mean, median, min, max, etc., and then replace the center pixel in the output image with the value mean, median, minimum, or maximum. This is how the order statistic filtering works. So once we have obtain the mean, median, min or max, then we move to the next position. Basically, we move the window like this to filter the values. Median filter is given by the expression f cap of x by equal to median of g of st, and it works well in reducing salt and pepper noise, as we have studied in the previous module. Next step of thing we can do with the order statistic filters is the maximum max filter, so which picks the maximum value within that sub image of g of st. And as we are picking the maximum value, it eliminates the dark noise or the pepper noise. It cannot get rid of the salt noise because we are picking the maximum value. Essentially, it picks the salt noise if at all it is present. And another modification we can do is minimum filter, which picks the minimum value within that sub image. So obviously, it eliminates the bright noise because we are picking the minimum value. So if there are pepper noise or dark impulses, then it will be retained, but brighter noise will be eliminated. Okay, so if there are no impulse noises in both cases in a min or max filter, so it will provide a good amount of filtration. Or if there is a other type of noise present, like for this max filter, if there is a salt noise present, or for min filter if there is a dark noise present, then it won't work properly, but in other cases it will work fine. And then we can have a midpoint filter, which is given by this expression, which is half into max of GFST plus minimum of GFST. So we add the maximum value and minimum value in that sub image and divide by 2. That is the midpoint filter. We have already gone through the working of median filter in the previous module. So let us once again revisit the concept. So median filter, as we know, is good for removing impulse isolated noise like the salt and pepper noise. So here is the image with the salt and pepper noise added. So salt noise is shown by the white pixel and the pepper noise is shown by the black pixel here. So what we do in median filtering is we consider a window of size 3 cross 3 in this case. So it's a moving window. So we recreate the pixels here. Then we sort them in ascending order. So when we sort them, basically the lower values move to the left here and the higher values move to the right. So low to high sorting we are doing, sorting in ascending order. So the black pixel moves to the left, that is the pepper noise, and the salt noise is on the extreme right here. And in median filter we pick the middle value like this, that is the median value, and that will be our output or the filtered output. Now the concept here is the impulse noise has high magnitude and is isolated, and when we sort pixels in the moving window, the noise pixels are usually at the end of the array, and therefore it's rare that the noise pixel will be a median value. And by this by picking this median value, we are basically eliminating these impulse noises, and that's how we get the filtered output. And we move window to the next pixel and then next, so we cover the entire image uh, to filter the complete image. Let us see the effect of using median filter multiple times on a corrupted image. So here is your test image, which is basically corrupted by salt and pepper noise with probability 0.1. Now if we pass this image through a median filter, this is the result. Okay, the improvement is significant, but several noise points are still visible. A second pass with median filter remove most of these points and leaving only few barely visible noise points here. Okay, you can barely see the noise points. And if you pass it again, okay, basically third pass, this is the result. Okay, these results are good examples of the power of median filter in handling impulse like additive noise. And we need to keep in mind that repeated passes of median filter tend to blur the image, so it is desirable to keep the number of passes as low as possible. Let us see the example of min and max filters. So here we have a image corrupted by pepper noise with probability of 0.1. Here note that we just added pepper noise, no salt noise here. Okay. Now if we use a max filter, the result will be like this. So it has eliminated the pepper noise, also made the image a bit brighter in the process because we pick the maximum values in the neighborhood. Now if you corrupt the same image by salt noise, okay, you can see the bright spots here, no dark spots, dark noise, it's salt noise, and you filter it using the min filter, we get this result. Okay, the image is a bit darker, but it has eliminated all the white noise in the image. Next type of mean filter is the alpha trimmed mean filter. So here the formula is f cap of xy is 1 by mn minus d into summation of gr into gr of st. Here gr of st represents the remaining mn minus d pixels after removing the d by 2 highest and d by 2 lowest values of g of st. So what we need to understand here is the term alpha trimmed means we are trimming the maximum value and the minimum values. Okay, some maximum pixel values and some minimum pixel values, and then considering the mean of the uh, neighborhood. So we'll see an example here. So we have pixel intensities like this. So we sort them, then we eliminate the highest values. Okay, so that is what we call alpha trimmed. This is the alpha minimum lowest value, and this is one more alpha highest value. So we are trimming those alphas. So alpha trimming is done here. Okay, and then we retain the uh, middle values and then consider the average, which is the mean. So that's why the name is alpha trimmed mean filter. So this filter is useful in situations involving multiple types of noise, such as a combination of salt and pepper and Gaussian noise. So let us understand the use of alpha trimmed mean filter with an example. So here we have an image corrupted by additive uniform noise, and then we additionally on top of this image we are adding additive salt and pepper noise. So it is having uniform white noise, uniform noise plus salt and pepper noise. Now if we use arithmetic mean filter with the 5 cross 5 window, and then filter it, so this is the result, and you can see the quality hasn't improved much. Okay, uh, so this is the input image and this will be the output image. Okay, now if you use 5 cross 5 geometric mean filter, again you can see the difference. It is different compared to arithmetic mean filter, looks somewhat better, means you can mark all the edges clearly here, but still the result is not so satisfying. Then again if we filter the image using 5 cross 5 median filter, so mind this is the input image, this will be the result. You can see it's much better compared to the previous two cases. Okay, uh, now if you use the alpha trimmed mean filter with d equal to 5, look at the result. So it is much better than the median filter also. Okay, so this is the power of alpha trimmed mean filter. Now let us compare them uh, together in next slide. So here is the comparison of all four images. So this is the arithmetic mean filter, geometric mean, median filter, and the alpha trimmed mean filter. And you can see the alpha trimmed mean filter works excellently compared to the remaining three. Even median filter fared a bit better compared to the geometric and the arithmetic mean filter when we have uniform noise plus a salt and pepper noise added to the image. So in this lecture, we have looked at periodic noise, estimation of noise parameters, restoration in the presence of noise only by using the spatial filtering techniques such as mean filters, order statistic filters, and the alpha trimmed mean filters. In the next lecture, we'll learn about adaptive filters and periodic noise reduction by frequency domain filtering. See you at the next lecture. Thank you.